So next lecture is on Fourier transform. So Fourier transform is something you are familiar with from your course on signals and systems. And we will start making a review of what you already know about the Fourier transform in one dimension. So the idea behind the Fourier transform is that any signal, and there are small details in there, like discontinuities cannot be well represented, and this is not a good example because it has a discontinuity. But aside from that, the idea is that any signal can be represented exactly, so with an infinite sum of signs. So you have waves, so a sinusoidal at the end is a wave. So you have a wave where you can control the amplitude, you can control the frequency and the position of that wave. So you can control the amplitude, you can control the frequency. So the frequency is the number of periods that, or it is related to the number of periods that wave has in a given amount of time. So for instance, in this amount of time, this wave has only one period, while this other wave has 4 periods. So the frequency of the one that has 4 periods is 4 times the one of the frequency of this one that has only 1 period. And the other term is the shift. So in general, so here you have it. For instance, let's go to here. Let's go here. Okay, so in general, when you have a sine, so you have x of t, that is our sine, has an amplitude, sine omega t plus phi. So this is the amplitude, this is the frequency, and this is phase. So the amplitude is how wide the wave is. So whether it is like this or like this. The frequency is what is the speed of that. So the speed could be something that changes like this, or it is much faster. And the phase is where it is with respect to the origin. So let's use a different color. So we can have, for instance, so we can have a wave that starts like this, or a wave that starts like this. So with respect to the origin here is a maximum, here it is a minimum, and it can be, or it is a 0, and it can be any value in between. And for instance, if we look at Fourier transform that we have there, this is a Fourier series. There are many kind of small details about that. Do you know the difference between series and transform? So the Fourier series has discrete frequencies, while the Fourier transform has continuous frequencies. So if you look at this one, this is the amplitude. So 1 over 2n plus 1 is the amplitude. The frequency is all this thing, 2 pi over lambda times 2n plus 1, and the phase is 0, because there is no term that is independent of time. And the thing is that by adding an infinite numbers of these waves, you can represent any signal. And so that is the main result of the Fourier transform. And just a reminder from your signal and system course. So this will be the notation we will follow. So for instance, if we have x of t, then the Fourier transform is x of j omega. And time is measured in seconds, let's say. What are the units of omega? The frequency. This is Fourier transform. So what are the units of omega of the frequency? Which one? Radianes por segundo. These are radians per second. And if we define, there are many ways of defining that. The definition of the Fourier transform is not unique. There are a few constants there that you can play with. So instead of that one, you could define one that typically is expressed like that. And when you use frequency, what are the units of frequency? Hertz. Hertz. Yeah. So this is measured in hertz. And you know that, for instance, for a wave, there is a relationship that is that the propagation speed of that wave is lambda times f. So lambda is the wavelength and f is frequency. So for instance, if you are talking about the electromagnetic waves, so this speed will be the speed of light, or the speed of light in the medium you are propagating. So for instance, if you are in a crystal, in a glass, then that would be the speed of light in that glass. And then lambda is in which units? Meters. And then frequency is in hertz. And what is hertz? It is the inverse of a second. So this is 1/second. Okay, so and then this is consistent. This is meters per second. That is that are the units of speed. Okay, so this is for a continuous signal. Then well, let's make some drawings. So for instance, here we would have this is my signal time x of t. Then I have this is my signal, and then the Fourier transform. Typically, this represented like this. This is to collapse. Like more space. So we have this is a time, this is x of t, and this is my signal. It goes from minus infinity to infinity, and then the Fourier transform. This is the omega axis, and this one, the Fourier transform is a complex. So the Fourier transform is a complex valued function. So you cannot. It has two parts: the real part and the imaginary part. So typically we represent only the amplitude, and typically it is represented something like this. So meaning the amplitude typically decays with frequency. So the maximum amplitudes are at the origin, and this is especially true for images. Maybe for standard signals, for instance, if you have a radio wave in radio communications, then the main band is shifted at higher frequencies. But yeah, for images, it is not the case. And then we have other kind of signals that are, these are continuous signals, but we also have discrete signals. So for a discrete signal, then what we have is this axis is n that doesn't have any unit, so those are indexes. And then you have these kind of deltas. What is this? What is the name of these deltas? No. Kroneker's delta. These are Kroneker's delta. Kronecker delta is defined like this. So delta n is equal to 1 if n is equal to 0, and 0 if n is equal to 0. So the Dirac delta acts in here. The Dirac delta is a continuous delta, so it is a delta here. And normally the symbol is an arrow rather than a circle. And actually, the definition of the Dirac delta is a bit more involved because it is not a function. It is something that the mathematical entity is called a distribution, and it is defined not as the Dirac, not as the Kronecker delta, that is a branch function, but branch in the sense that it has two branches. But it is defined through its properties. So the Dirac delta is a distribution such that when you integrate this, you get x of 0. So that is the definition of the Dirac delta. So it is something. This something is a distribution. It is not a function. Typically, we say also a function, but it is not truly a function. So it is something that when you integrate another signal with a shifted delta, what you get is the value of that signal at the value of this. Okay, so this is Dirac. Okay, so now we have discrete signals. So what is the discrete Fourier transform? So when you do the Fourier transform of this transform, what you get is something that is more or less similar to what we had before, but now it is represented like this, and this is the omega axis, and now little omega. And there is another property of this Fourier transform that is not fulfilled by the continuous Fourier transform. You may remember. It is periodic. So this Fourier transform is periodic. So it repeats every 2 pi, and the same on minus 2 pi. Okay, and it goes from minus infinity to plus infinity. It is repeating every 2 pi. Yeah, now, n, we said it doesn't have any units. If we want to put some units, we could say these are samples. What are the units of omega, little omega? Radians per sample. So this is radians per sample. Better brackets, square brackets to represent units. Okay, another important notation thing, that is discrete variables are represented. Discrete variables are represented with a square bracket, while continuous variables are represented with parentheses. And another very important notation thing, try to be consistent with the uses of frequencies. So for continuous frequencies, try to use j omega, and you see that we are using parentheses, meaning that this signal in the Fourier space, it is continuous. This one is continuous in real space. This one is continuous in Fourier space. And here we have the same. This one is discrete in Fourier in the real space, But this one here is continuous in Fourier space. And try to be consistent with the notation of whether this is a discrete Fourier transform or a continuous Fourier transform. Okay? So all the notation stuff clear? Good. Okay, so then we move on to the next slide. So yeah, this is just the same that we had before, and the Fourier coefficients. So actually, yeah, let me copy this one. Y si yo quiero recortar.
Es posible que abajo a la derecha y todo. Si me dices que es como un más a la derecha.
¿En este?
No, más. Después del.
¿Aquí abajo?
No, el simulador que es como un bocadillo con una luna al lado del reloj abajo a la derecha.
Este.
Más.
Este.
Sí. Es que me suena que a la derecha suele salir una opción en expandir abajo a la izquierda.
Abajo, que expandir.
Recorte de pantalla a la derecha.
Oh.
Y ahora puedes elegir más específicamente.
Oh. Lo que es saber, ¿eh? Bueno. Okay, so okay, so now if we look at this expansion that we have here, these things here, they are called the Fourier coefficients. So this is a continuous signal, so this is x of k omega. So those are the coefficients. In this particular case, they are real valued coefficients. But and these ones here, they are the basis functions. So the basis functions. So in general, any Fourier transform is a multiplication of some coefficients, some times some basis functions. So these basis functions, they have some properties we will see later, but the main property is that, one of the main properties is that they are orthogonal to each other. And we will define the concept of orthogonality. Okay, so we are not here. Okay, so these are the basis functions, these are the Fourier coefficients, and so on. And then the more coefficients we add in this summation, so look at here, we have a sum from minus infinity to infinity. So the more terms we add to that summation, the closer we get to the signal we are trying to represent. And in principle, if we add the infinite signs, we would get an exact representation. This is not true for the square wave, because at discontinuities, so there is this discontinuity, we have something that probably you remember the name. What is this oscillation at discontinuities? Is the name of that? Gibbs oscillations. So at discontinuities we have Gibbs oscillations, and that is why we cannot represent exactly signals with discontinuities. But otherwise, we would not approximate. We would get exactly to the same input signal. So yeah, this is the main idea that I showed you before. So when you have a wave, or a sinusoidal wave, you have 3 parameters you can touch. One is the amplitude, the other one is the frequency of the period, and the other one is the phase shift. And in general, so for instance, here, if you have this expression, what are the units of lambda here in this expression? Seconds. Yeah. Remember that the argument of a sign has to be radians. So these 2 pi are radians, phi is in radians, and then t over lambda has to be unitless. So t is seconds, so lambda has to be seconds too. And then we said the basis functions are orthogonal. So you need to define the concept of orthogonality. And let us go back to here. So for instance, you have these 2 vectors. Let's say we have the vector -1, 1, and we have also the vector 1, 1, and we say that those 2 vectors are orthogonal because the dot product between the 2 is 0, and the dot product is the -1 times this 1 plus this 1 times this 1, and this is -1 plus 1, that is 0. So in general, 2 vectors, v1 and v2, are orthogonal if the dot product is 0. The dot product is also represented like this, with angle brackets. So, and in general, if you have, so this dot product is defined, so the dot product between v1 and v2 for R2 vectors. So for vectors that belong to R2, the standard dot product is the following. So v1x times v2x plus v1y times v2y. Do you agree? Yeah. Okay, so this is for standard vectors. So Rn vectors. So what about functions? So we need to define another dot product between 2 functions. So let's say I have, excuse me. So let's say I have 2 functions like f of t, and this is t, and this is my function. And I have another one that is now g of t, and this is my function. Now it is like this, and I want to compute the dot product between those 2. So a possible definition, it is not the only one, but a possible definition of dot product would be this one. This is a comma. So it is the integral of the pointwise multiplication of the 2 functions. And then we can extend this concept to more sophisticated scenarios. So for instance, what if f and g are complex valued functions? Then I can define my dot product by using the complex conjugate of g. Okay. And what else? What if my function is periodic? So if my function is periodic, then I should limit that multiplication it goes from minus infinity to infinity of a periodic signal, so it will be infinite most likely. So I should restrict my integral to just the area where it is aperiodic. So I concentrate in the main period of that function. So lambda is the wavelength. So it is a, remember that if you have a periodic signal, it doesn't need to be a sinusoid, so it can be whatever. So let's draw this one. So this is this is my period. Okay, so I'm going from minus lambda half to plus lambda half, and then I'm multiplying the two signals, and this will be the dot product, the inner product between my two signals. So now we can define orthogonality. So I can say two signals are orthogonal if the dot product between the two, is 0. And for instance, you can imagine, for instance, let's put an example of orthogonal signals. So let's say that f of t is a constant signal, and this is t, and the other one, g of t, is a sinusoid. We are integrating only from minus lambda half plus lambda half, so we are going from here to there. Minus lambda half plus lambda half. And the multiplication of these two, this is a constant, this is just 1. This is just 1, let's put some numbers here. So this multiplication this is a constant, this is a sinusoid, it is just a sinusoid. And now I'm integrating from minus lambda half to plus lambda half. So I'm integrating here this area. And what is that area? This here. So those two signals are orthogonal. Okay, so now we have the same thing, but now in slides. Yeah.
No entero.
¿De qué?
De por qué son ortogonales.
Pues porque cuando yo defino el producto de las dos, fíjate, f de t por g de t, como f es una constante, pues es g de t. Y ahora estoy integrando de menos lambda medios a lambda medio. Luego tengo que ir desde aquí hasta aquí.
Vale.
Y esa integral vale 0. Okay, so now, yeah, so this is the same, but now put in the slides. And here you have some examples. So for instance, let's say that we have this f, we have g now in blue, and we have the product, well here we have f and g, and now we have the product of f times g, which is this red curve, and now I'm integrating from here to there, and that is the area that participates in the inner product. Okay? So I did it for a very simple example, but now this one is made with the computer, it is much easier to show. Okay, so now we have a different example, now with f with h. So f with h, so yeah, this says g is a component of f. So g is a component of f means that this area is different from 0. And now h is not a component of f. So now this area will be 0. Okay, so now let's look at the Fourier transform. So let's say that I'm computing the inner products between any function f and my basis function g. So my basis function g will be the basis functions of the Fourier transform. So we can define the Fourier transform in different ways. The most convenient way is with the complex exponentials, but we can also use sines or cosines. And actually, this you may recognize as the Fourier series that probably you have studied. So now we are computing the inner product between f and the basis of the Fourier series. And the one for the Fourier transform, we can put it like this. So I will forget about this representation, or otherwise we go from here backwards. So now my basis function is this one. It is the complex exponential. I have defined omega as 2 pi over lambda, where lambda is the period. And then if you go back, I can decompose this omega as 2 pi over lambda, so you have an equivalent expression. And here what you have is you have this Euler relationship that expresses complex exponentials as complex numbers that involve the cosine and sine. So this you probably recognize much more easily in this way. So let's say that we have a jx is cosine of x plus a sine of x. Okay, so this is the Euler relationship. And actually, now you start recognizing why the Fourier transform has this x over a omega. It has the same structure. This argument and this argument are the same. Okay, so I think the easiest way to reason about this is you start here, which is the standard definition of the inner product, and then if you want, you start substituting things. So you take the 2 pi over lambda, and then you have this expression. This is a different, but totally equivalent expression of this one. There is another Fourier transform that uses, instead of that one, instead of making so let's write the one we have now. So we have the integral from minus lambda half to plus lambda half of f of t x minus k omega. And this would be x of yeah, and if we are in the continuous world, it would have been better to use the continuous Fourier transform. But we may use this one, or we may use now this other one. X of f is the integral from minus lambda half to plus lambda half of f of t and n. So I could have defined the Fourier transform in this other way, and it doesn't matter. It has the same kind of information. The axis is a little bit different, but the information that we have is the same. So yeah, so this is just a matter of notation. So depending on the book that you are reading, some authors prefer this one, some authors prefer this one. Okay, so next. Okay, so now if you look at this integral, we are multiplying. So what is the basis function? This is the complex conjugate of the basis function. So the basis function is this one, but with a plus sign. Okay. The other important observation is that we are making an integral in which this is a real number and this is a complex number. So we are summing an integral and a summation is the same. So we are summing many complex numbers So at the end, the result will be complex. That is why the Fourier transform is a complex number. Okay, good. So then, so what if can I relate the complex number that I get from the Fourier transform to the real numbers that I get from the Fourier series? So the Fourier transform takes a signal and computes complex valued coefficients, while the Fourier series takes a signal and computes real valued coefficients. And the trick is that it decomposes, it separates these complex basis function into its two cosine and sine representation, and then here we are using somehow that there is a symmetry if there is a symmetry that probably you also know, that is if x of t is real valued, then x of minus j omega is equal to x of j omega complex conjugate. Do you remember that? What is the name of that symmetry? Hermitian symmetry. This is Hermitian symmetry. It comes from a guy called Hermite. That was a French, I think he was French, mathematician. If you are coming from the optics world, this is called also the Friedel symmetry. So if you read optics books, then they refer to this symmetry as the Friedel symmetry. Okay. So by exploiting that symmetry, we can combine the coefficient of lambda and the one of minus lambda, or omega and the one of minus omega, to get this kind of real value representations. Okay, and here you have how these Fourier coefficients now they are calculated. And there is a relationship between all those terms. That is, for instance, this phi n here is the phase of this complex number Cn. Okay, so Cn is defined in this way. That is almost the same that we had before. Almost the same that we had before, but now we have here this 1 over lambda. So it is almost the same. And now this is a complex value. So this complex value will have an amplitude and a phase. So this phase can be represented in that way, and those are the numbers that go into the cosine and sine. You see? So the coefficients that go in front of the Fourier series is the module of Cn, and then inside the cosine and the sine, you have the phase of the Fourier transform. So this is the Fourier transform, and this is the Fourier series. Then, this is the same idea. So now, what is the interpretation of this phase? So the interpretation of this phase, it is given by the Fourier series. So the Fourier series says, okay, so the amplitude of the cosine and sines is the module of the Fourier coefficient, but the phase is where that wave is starting. So whether we should shift it to the left or to the right. So it is given by the phase of this complex number. So now this phase shift is just this number here. So, Fourier transform. So the Fourier transform is defined in this way. And you may recognize, actually, the Fourier transform, the way we normally use it in books is the opposite. So it doesn't matter again, but it is a matter of definition. It is more convenient, and it is more custom to put here the minus and here the plus. Okay. So let's look at it here again. So we have the continuous Fourier transform. So the continuous Fourier transform is x of omega of j omega is the integral from minus infinity to infinity. Now we forget about periodic signals and we extend it to any signal. Remind that the Fourier series is only defined for periodic signals. So now we have here x of t this is omega differential t. And we now recognize here what it is. This is my basis function. This is my basis. The basis, some other context, it is also called the probe function. So that is our basis. And all this is simply the inner product between x of t and my basis function. What about the inverse Fourier transform? The inverse Fourier transform, let's put it up. So the inverse Fourier transform is, aside from some constants probably, but this is the main part that I want to highlight. And this goes again from minus infinity to infinity. But now, let's look at this. Let's look at this. So this is equal to, this is the Fourier coefficient. But the Fourier coefficient is this thing. Okay, so I will write that thing. So it is x of t times my basis function. So at the end, the Fourier transform is a sum of a lot of basis functions times some coefficients. And this has the same structure as the following. So let's think, when you write this vector, so let's say that you write my vector v is 1, 3, 1. What you are saying? So what you are saying is that this is 1 times x, let's say, plus 3 times y, plus 1 times z. And how did you come to these 1, 3, and 1? Well, because you have x, y, z, you have x, y, z, you have your vector there, and this 1, 3, 1 is this 1 here is the inner product. It is the inner product between v and x. This one here is the inner product between v and y, and this one here is the inner product between v and z. So you have actually the same. So you have the inner product of your vector times your basis, then the inner product of v times your y basis times the basis. So you have the same structure than there. So the Fourier transform is only a change of basis. So instead of having the standard basis that is the delta function, so for when we have this signal here, this signal, you can think of it as many Dirac functions, one at the side of the other. So you can think of this as the integral from minus infinity to infinity of x t0 delta minus differential. So those would be your inner products, which is x of t times delta t minus 0. And now this is my basis. And I have the same. So now I'm changing from a basis of deltas to a basis of complex exponentials. So the Fourier transform is simply a change of basis. I think this is enough for 1 hour, so let's make a break. ¿Alguna pregunta a todo esto? Todo esto no es fácil, ¿eh? Bueno. Okay, so we continue with the next. So, Ana, contadme un chiste. Uy,
Para de...
Porque la escoba siempre está feliz, porque va bien.
Es un poco verde, pero bueno, bastante igual. Se abre el telón y aparece ahí una señora en el váter haciendo un esfuerzo terrible que le dolía un montón la tripa. ¿Cómo se llama la película? A Pretty Woman.
¿estás pensando qué?
Sí.
Pues mira, ¿cómo era?
No hay un pájaro que te drogas, la que te drogas eres tú que hablas con los pajaritos.
Pero mira que te he dicho 10.000 millones de veces que no exageres.
Te gusta el rock progresivo cada vez más. Como maldijo un pollito a otro, Calvito es tú.
¿Pero alguien? Ah, venga. Claudia.
Porque estaba buscándolo y no me lo sé.
¿Es crónico ya?
La siguiente te lo meto.
A mí no, al resto.
La siguiente.
Bueno. So, the Fourier transform is simply a change of basis. So, this is the definition of the Fourier transform. We have used a different one with the minus here. And then in the inverse Fourier transform, you have to put, instead of minus, you have to put plus. But it doesn't matter which one you use as long as you are consistent. And then this integral here, in general, will be a complex number that we will present as f omega. And this complex number will have a module and a phase. Okay, and this is just different variations of the same idea, but the idea is that. Okay, so something very interesting of the Fourier transform is that when we hear some sound, we are implicitly doing a Fourier transform of the sound. So, for instance, you have some sound pressure wave, and this sound pressure wave, if you look at what is the, for instance, the displacement of a membrane with respect to its equilibrium position, this is actually the physical construction of microphones and loudspeakers. You have a membrane that has some position at rest, and then it vibrates, and this vibration either it emits sounds, or in the microphone, it is recording the displacement of that membrane. So if you record what is that displacement, for instance, this one would be something like this. Okay, so that is a rapid transition, and this is okay. So at the end, in the ear, we have something that makes the Fourier transform of this input signal. And this Fourier transform, we are only sensitive to the amplitudes. So you may do this experiment in MATLAB. So you record a little bit of your voice, you do the Fourier transform, you shuffle the phases of that Fourier transform, and you do the inverse Fourier transform. And you barely listen to the same voice that you recorded. So there is no, we are not sensitive to the phases of the waves, of the sound waves, but we are sensitive to the phases of the waves of images. So we will see that later. Okay, so now we have the same definition that we had for continuous signals, but now for Fourier, for discrete signals. So now let's say that, let's make it here. So we have defined the inner product for continuous signals, but now we will define it for discrete signals. So let's say that we have two signals. For simplicity, we will assume that they go from 0 to n minus 1. So, and then they are 0 everywhere else. And the same for another signal. Let's call it y, for instance. So we have it to n minus 1. So the last sample that is different from 0 is the n minus 1. And then we have to define the inner product between these two signals. But now it is much easier, because the inner product, so following the spirit of the previous inner product, so the previous inner product was an integral where the signals were defined. So now we can make a summation where the signals are defined. This would be our inner product. And if we want to be fancy and we want to make y to be a complex value signal, then we do the same trick as we did before. We calculate the complex conjugate of that. Then what is the Fourier transform? So in this setup, the Fourier transform, but now the discrete Fourier transform. So I have to compute a discrete Fourier. So I need to define a signal that goes from 0 to n minus 1. So yeah, actually, we don't care. We don't care. This is correct, but the one I'm going to write now is also correct. So we can go from minus infinity to infinity. We have any signal in there. Okay, so now I need to define the inner product. So the Fourier transform is the inner product of my signal with some basis function, and that is what I have to define. And the basis function that has been found to be useful in this context is this one. Okay. Is this one. Okay. And n is this. So your signal is defined between 0 and n minus 1. So you have this there. Actually, it doesn't matter if you put minus infinity to infinity or 0 to 1 minus 1. 0 to n minus 1. So, but now these are my basis functions. These are my basis functions. And the inverse Fourier transform, how many of these functions I have? I have as many, I have a continuous. I have a continuum between 0 and pi. Or if you want, between minus pi and pi. And the reason for that is that it is periodic. So actually it has to be open on one side. So let's make it open on one side. So you know, a square bracket means minus pi is included. The parenthesis pi is not included in the interval. And the reason is that these signals are periodic. So if I use an omega that is different from outside of this region, I get exactly the same flow. I get exactly the same basis. So that is why this signal is periodic. This Fourier transform is periodic. So now let's recover the original x of t. So the inverse Fourier transform. So the inverse Fourier transform, my Fourier transform is a continuous or a discrete signal. The Fourier transform is discrete or continuous? Discontinuous. So instead of a sum, I need to do an integral. It is the integral from where to where my basis functions are. So I have this range, so it has to be from minus pi to pi of my Fourier coefficients times the basis function. And the basis function is this one. And now differential of omega. So I have the same structure as before. So those are my coefficients. So those are the image products that we had before times the basis function. So all the time we are having the same structure, that we are making a change of basis. But now we are going from a basis on real space that is a set of deltas, but deltas, Kroneker's deltas this time. So if you think of your x of n, what we have are Kroneker's deltas. So we are going from the basis of Kroneker's deltas to the basis of complex exponentials. And this change of basis is so easy because these bases are orthogonal. So if you take any two, I will write it for the discrete signals, but it also holds for the continuous basis. So if I take any one of these two bases, omega 1, omega 2, this is equal to 0. As long as omega 1 is different from omega 2. And the same holds for the continuous signal. So if your bases are orthogonal, then moving from one base to the other is as simple as this thing. If they are not orthogonal, it is a bit more complicated. Okay, so yeah, this is what I have said is what you have here. So this is the discrete Fourier transform, and you recognize here the. So those are the Fourier coefficients. Those are the Fourier coefficients. This is the inverse Fourier transform, and this is the forward Fourier transform. Okay, so why do we need Fourier transforms? Okay, so this is just a reminder of the same thing. And this is the orthogonality that I have mentioned. Okay, so if you have two basis functions that are that do not have the same frequency, they are orthogonal to each other. Okay, so all this is redundant with what we have said. Okay, so now let's look at. I will rewrite this part in a different way. Okay, so all this has been for 1D signals. What about images? Okay, so let's look at the Fourier transform again. So I will write the Fourier transform again now in the, let's do it in the continuous domain. Sorry. So in the continuous domain, Fourier transform was the integral from minus infinity to infinity of x of t. This is a 1D signal, so this is a 1D. What does it mean that it is a 1D signal? That this function goes from R to R, and this R is 1. This 1 is what makes it 1D. Now, if I have a 2D signal, so if I have a 2D signal, I will have something like this. So x. X is not the good name for. So let's say we have y of x and y, and now I is a function that goes. Make it red. So I of xy is a function that goes from R2 to R. So this 2 makes it 2D signal. Okay, so now I don't have an argument anymore that is t. I have two arguments, x and y. So, but we can play the following tree. So let's make, okay, I will write it. And this will be r. This will be definition of omega. And okay. So what have I written there? Okay, so I have defined the following vector. I have defined the vector position that is x and y. Now I have defined another vector. So now instead of having one frequency that is a scalar, so here we have a frequency that is a scalar. So instead of having a scalar frequency, what we have is a vector of frequencies, and we will have a frequency in x and a frequency in y. And what I have here is the inner product between the two. So the inner product between the two, so r times omega is x times omega x plus y times omega y. And now if we compare the two, we have the same structure in the two. So this is the inner product between vectors of one dimension. This is the inner product between vectors of two dimensions. Actually, this is the general definition for the Fourier transform in n dimensions. So you have the inner product between a vector of frequencies and a vector of positions. This is the same that we had before. And before I was integrating over all time, Now I have to integrate over all positions. And that's it. And now this is my Fourier transform, but now in 2 dimensions. And instead of having a frequency that is a scalar, now I have a vector of frequencies. So I have 2 frequencies, one in x and one in y. And we will see examples of this so you understand better. But the definition is the same. And the inverse Fourier transform is defined in a similar way. So the inverse Fourier transform is made of real. So if I want to recover, this is a bad name, this one. It should be the Fourier transform of I. So if you use capital letters for the real space signals, then you put typically a hat for the Fourier transform. So the inverse Fourier transform now is defined as the integral over all frequencies. This integral is in frequency of the Fourier transform of your image, and then so it has the same structure as we had for the inverse Fourier transform of 1D sequence. And again, remind that this is simply the inner product between your image and your probe. And the probe here is just this one. Okay, good. So now we have 2 discrete transforms also for images, and they have the same structure as they have for 1D sequence. Okay, so let's see some examples. So this is the same. You can see this is my probe now. So instead of using omega x, omega y, they have used u and v, but it is the same. I prefer omega x and omega y because I think it is more clear with which u goes with x, v goes with y. And then you recognize the same kind of discretization for images. So for instance, I have explained it for continuous images, but you can imagine that we can make the same for discrete images. So if I have an image that goes from 0 to n minus 1 in x and 0 to m minus 1 in y, then these probe functions, so this omega, now it is a discrete, so I will make it small. So I can define it as 2 pi over n, because it goes in x, times some k, kx, and then 2 pi over m times ky. And kx and ky, they go in the set 0, 1, n minus 1, 0, 1, n minus 1. So now this is the discrete version of that, of those frequencies. Yeah, I haven't explained actually this. The way I explained it before, these ones were continuous. Now they are discrete. And it is the same as, you have studied the fast Fourier transform, right? Have you studied the fast Fourier transform? Okay, so let's come back again to one dimension. and see where the fast Fourier transform comes in. Okay, so we have said, we have a signal that goes from 0 to n minus 1 samples. And we have said this one has a Fourier transform that is periodic. So it's periodic with period 2π, and the same of minus 2π. Okay, but now I cannot store that in a computer. So what I can do in a computer, so this is the discrete Fourier transform, this is the discrete Fourier transform, but I cannot do that in the computer. What I can do in the computer is something different, that is called the fast Fourier transform. So the fast Fourier transform assumes that your signal is periodic. So instead of working with this signal, it works with a different signal that is related to that one, that is x periodized. Okay, so I take the x that has this pattern, and then I make it periodic. And on the other side, the same. You make it periodic, and automatically the Fourier transform that you have is the one that you had before. So I will repeat the same. But now you are taking samples. And if you are keeping just the central samples, so for instance, the ones that go from 0 to n minus 1, then I can exactly represent this periodic signal. Okay, so now my frequencies that here they were continuous, and they were this. Okay, I don't remember anymore which is the letter I used before. Omega 1. Actually, it wasn't a good letter, but so let's make it so this K was a continuous. Now the green frequencies. The green frequencies, they are not like continuous anymore. But now this K goes from 0 to 1 So there are many subtle details in the Fourier transform. So let's try to recapitulate a bit so that we see a better picture of what we are doing. Okay, so we have continuous signals and we have discrete signals. We are now concentrating on the discrete signals. So the discrete signals, the discrete Fourier transform of the discrete signal is something periodic. But that is not what I can store in the computer. What I can store in the computer are just samples from these continuous Fourier transform, and then these samples will be called the fast Fourier transform. And the frequencies associated, they are not any, but the ones that fulfill this equation there. And what else? What are these delta functions? They are Dirac's or Kronek's? This. Dirac. They are Diracs. They are Diracs because they are coming from a continuous signal. So whenever you sample a continuous signal, what you get is a Dirac delta. And if you are in the discrete world, then you have a Kroneker's delta. Okay, good. So now you understand what you are having there. So why it is written in this way? Why these indexes, they go from 0 to n minus 1, from 0 to n minus 1, and they're also orthogonal. So if you take two basis functions that do not have the same frequency, then the inner product between those two is 0, and they are 0 for the continuous Fourier transform and for the discrete Fourier transform. And here you have, what is it? Yeah, the definition of the Fourier transform. So this is the inverse Fourier transform, and this is the forward Fourier transform in the continuous. So all this is continuous, all this is discrete, but we have similar definitions as we had before. And here are some examples. So let's say that we have this is the forward Fourier transform, and this is the inverse Fourier transform. So we have an image, and we can think of this image as lying in an infinite plane. So when we are saying, for instance, here, when we are saying at this point, what is it? Here, when we are saying you take your image and you integrate from minus infinity to infinity, so that is for absolutely all locations, you can think of it as lying in a plane, and this is the xy plane. We have to go from minus infinity to plus infinity, but only a part of this plane is occupied by our signal. And if you, yeah, this is more complicated. So this is a discrete image now. So we have here Kroneker's deltas, and this is the definition of the forward Fourier transform and the inverse Fourier transform. And the representation of the inverse Fourier transform has been done like this. So this is true. So the representation of the periodicity, it is done like that. It is true, but I think it is too complicated. So let's say that we have our signal here. So we have our image. So we have our image here. And for the continuous Fourier transform, there is no problem. So this image lives isolated in the world, and everything outside is 0. But what about the fast Fourier transform? So the fast Fourier transform, we have to make it periodic. So this is x and y. So we have to make it periodic. And to make it periodic, one possibility is the one that he's showing in the slide. The other one is the following. So I can make periodic by I take this image, and then I make it periodic. Let's choose it blue. The same everywhere. And it goes infinitely in all directions. Okay, so this is my periodic image, and this is the one that I'm computing the Fourier transform. So, what is the relationship between this periodic image and the torus? Okay, so let's say that you take this location, or better, this location here, and I start traveling to the right, at some point I get out of my original image and I start seeing the same values that I would see here. And the more I travel into that direction, the more these points are equivalent to these ones, right? This is the definition of periodicity. And at some point, I will reach the nose. Okay, so that is exactly the same effect that you have in the torus. So if you start at this point and you start traveling up, at some point you get out of your image, but it is the same as if you go down and keep traveling. So that is what happens if you put your image in a torus. Okay, so you will be traveling on this direction. So making the analogy with the torus or explaining the Fourier transform in the torus, I think it is too complicated to think. I find it more convenient to think in terms of periodicity. Okay, so I repeat my image infinitely many times, and then I'm computing the Fourier transform of that. Question? No? Okay, then. Yeah, so those are same things. Like this is the inverse Fourier transform. This is the forward Fourier transform. In my expressions, we have disregarded this kind of constants. So this kind of constants is just to make the summation be correct, but otherwise we don't care about that. Okay, so what is a 2D sinusoid? We have said these kind of signals here that are my probes. How do they look like? So I can decompose those 2D waves, or I can express those 2D waves in different. I can manipulate algebraically that thing. So for instance, let's say V and U are the frequencies. Okay, so this is U, that is the frequency associated to X, to the columns, and this is V, that is the frequency associated to the rows. The rows are Y. And then, given a VU point, I can express it in polar coordinates. So I can say, okay, this is your UV point, but this has some module that has some angle with respect to U. So now I can write U as omega cosine theta and V as omega sine theta. And I can compute what is this omega and theta. So omega and theta come from, this is the module of the UV vector, so it is U squared plus V squared, square root of that. And theta is the arc tangent, so it's the arc whose tangent is V divided by U. So this is cosine divided by sine. Then I can define, for this manipulation I don't need it. So now I substitute these U and V expressions back in here. And this is what we get. Okay, now we can define the wavelength as n divided by W. And then wherever you see W, that is only here, you put you solve for W here, so you write n divided by lambda. So n divided by lambda, this was divided by n, so the n cancels, and then you have this thing. Clear? Okay, now you can take the real parts and the imaginary parts of this complex exponential. This is the same as we did before with the Fourier series. Let's go back to one dimension. In one dimension, we had also the complex exponential, but we had also in the Fourier series, we had cosines and sines. So those are the real and imaginary parts of the probe function. Then we are here, yeah, and there is some explanations here. So 2 pi omega divided by n is the frequency in radians. So the units is radians per sample. Omega divided by n is another frequency, but now the units are not radians, they are kind of normalized frequency. Actually, this one, it goes from minus pi to pi, this one goes from minus 0.5 to 0.5. It is the opposite, right? This omega goes from minus 0.5 to 0.5, this one goes from minus pi to pi. And then we can define this lambda that was defined before. So it is the wavelength in pixels in the wavefront direction. So let's look at some pictures, that is easier. So a 2D wave, let's take the real part, that is the one that we can represent, for instance. We cannot represent complex signals, so we can represent only real valued signals. So let's take the real part. So a 2D wave is a wave in the same way as a 1D sinusoid is a wave. And it has the same parameters or the same features as the 1D waves. So they have an amplitude. So an amplitude is the number that goes in front of the wave, and it determines how wide this wave is. So how large that is in terms of intensities. The other one is, the other parameter is the frequency or the period. We know that they are related. So the period is the difference between the distance between two equivalent points. So if we look at the maximum, then what is the distance to the next maximum? And the other one is now we have two frequencies. You may remember that before we had only R. So let's look at the 1D wave. So in the 1D wave, we have a single parameter for the space. The space equals something like sine omega t plus phi. So we have a single real space variable, but now we have two real space variables. And now our waves look more like this. Actually, I will write it to so let me write it first like this. So this is 1D, this is 2D. And this is equal to, and this is equal to this, sine of omega x plus omega y plus phi. I prefer this notation where you see clearly what is the frequency, rather than U and V. U and V, I find it ambiguous. But okay, so now we have two frequencies rather than one. So that means, look at here, this R and C is X and Y. Okay, so R is Y, C is X. So R is the row number. Rows go like this. So this is Y, and C is the column number. That is X. Okay, so now we have two numbers that are multiplying. One is multiplying R, the other one is multiplying C. So those are the WX and omega X and omega Y. And we have a single phase. Okay, so let me go a few slides more, and then you will understand these frequencies. Okay, so one of the parameters was the phase shift. So the phase shift, as before, it is where the wave starts. So at the origin, do we have a maximum? Do we have a zero? Do we have whatever value? So this phase shift is shifting the wave along the direction of the wave. Okay, and the other one, I hope that I had something. Yeah, that's something for that. Okay, we will come later to more details on omega x and omega y, but let me show here a detail. So let's look at these axes and let's look at this one. Okay, so we see here a periodicity. Can you see that? Here we have a maximum, another maximum, another maximum. That is the lambda associated to omega x. And then in y, we have this maximum, this maximum, this maximum. And this is the lambda associated to y. So those are, so once you have two frequencies, one that is multiplying r, another one that is multiplying c, these two numbers induce two different wavelengths, one in x, one in y. But the period of the wave is a single one, that is in the direction of propagation. Okay, so this lambda is in the direction of propagation. Actually, this is not correct. This is lambda in the direction of x, and this one is sorry. So the true lambda is in the direction of propagation, while this one is lambda x, this one is lambda y. There are more drawings later, more figures that will learn this. Okay, so there are three periods here. There are three frequencies involved. So one is the lambda and frequency in the direction of propagation. The other one is the frequency and lambdas in x and y. Okay. And because the lambdas can be different in x and y, now we can turn our wave to travel in whatever direction we want.
And the lambda in the direction of the propagation is a composition of the orthogonality.
Yeah, you can compute from lambda x, lambda y, you can compute that. Yeah. But it is easier to compute lambda in this way. So I'm just, well, it is just time, so we can continue tomorrow. Okay, good. Now, yes, here we go.